Greetings, math friends. I've been working on some different aspects of mathematics based on a question that I was asked, and I just went down a couple rabbit trails on some things, and I've come to this integral that I wanted to do, and I was struggling with how to do it. I had had a few failed attempts, and I looked in one of my old calculus books, and then I looked in my reference guide here. I have a standard mathematical tables. This is published by CRC, which is the Chemical Rubber Corporation. This is published in Ohio, Cleveland, Ohio. And it has tables of integrals in it, like your calculus book might have. And I was able to find a series of logarithmic integral forms here that I was able to apply to this and find a solution. I knew what it was supposed to be, but I was struggling to get there. Having used these, which I called theorems, which essentially they are, I then went back through and tried to figure out where my mistakes were. So one of the things that I ended up doing is I created a new integration by parts theorem, which I want to derive here, and then try to use that new theorem to solve this integral. If you have had an analysis course or an advanced calculus course where they focus more heavily on the theory and why things work, you may know how to derive the integration by parts theorem. There are videos out there about that if you're unfamiliar with that, but I want to go through my own process here and how I derive that and try to apply that to solving this. We're going to start with three functions of x: u of x, v of x, and w of x. And we're going to take the derivative of this with respect to x. So we're going to apply the product rule here. We have u times the derivative of vw dx, and then we're going to add to that vw times the derivative of u with respect to x. We have to deal with this differential of vw over here, so off to the side we are going to look at that. We're essentially doing the same thing that we started out here, only with two functions instead of three. So we have v dw dx plus w dv dx. All right, and then we're going to just substitute that in over here. So we have u times v dw plus w dv dx. All right, then we're going to distribute the u function across this. All right, and this is all the derivative of this. So UVW prime is this. Now we are going to integrate this with respect to x. All right, and these differentials here, they will settle out. If you look at an analysis book like Binmore's, he takes the time to make this rigorous, that these will come out to be just du here, dv, and dw here. This is an inverse operation here, so we come back to having uvw is equal to the integral of uv dw plus the integral of uw dv plus the integral of vw du. You can kind of see the traditional integration by parts formula start to show up here. We want to switch these places here. So we are going to subtract this from both sides and subtract this from both sides. And then we're going to multiply by through a negative so that this, which would have been a negative when we moved it, will become positive again, and then all these signs will change. So we have the integration of uv dw is equal to uvw minus the integral of uw dv minus the integral of vw du. All right. So this is an integration by parts extension theorem. And I'm going to use this essentially as a lemma to help me integrate this integral here. So I want to move this up and then start applying it to this integral. And this has this is a definite integral, so we will eventually have to place limits on our integration here. Something I want to do to this as I get started is I want to take this negative through the integrand. So I want to pull this -1 to the third power out here and have log t cubed dt. And then further, I'm going to separate this as the log of t times the log of t squared dt. So I'm separating out by multiplication here. So now I'm going to have that log of t is going to be u, log of t squared is v, and then dt will be my dw, which fits this. So then I'm going to take the derivative of each of these and integrate this so that I know what my du, my dv, and my w is to plug into this. So as we take the derivative of the log of t, I end up with 1 over t. And then looking over here, take the derivative of log t squared. This is 2 times the log of t. And then we have to multiply by the derivative of the inside, which was just this first one. And then we have that dw is equal to dt. If we integrate on both sides, we will see that we just get those variables back. W is equal to t. So then we can take these, clean them up a little bit if we want to, and substitute them into this. So the first thing that we need is UVW. U again is this, V is this, so it's this original piece, the log of t cubed, times W, which is t. And then from that, we're going to subtract the integral of U times V, U times W. So U again was log t. W is t. And we want dV, which is this. forgot my differentials. So we have 2t inverse log t dt. And then I'm going to subtract. All right, this is what I get when I substitute my u, my v, my dw, my du, and my dv into my lemma here. This is equal to this, and only this part is this. So I have to have this negative 1 to the third power that's going to act as a scalar over this. And there's lots of things to clean up in here, and I'll do that as we go through the process. So looking at just the right-hand side here, if I evaluate this at 0, this goes to 0. And if I evaluate it at 1, it also goes to 0. So this is not contributing anything in magnitude to this. For now, I'll go ahead and write a 0 in there. As we look in here, the t's are going to cancel here. I'm going to have log t squared here, and I'm going to have an extra 2. I can pass that through the integrand. Looking over here at the next one, these t's will also cancel, leaving me with just a log t squared. And now I can add these two pieces together. So I have -2 plus a -1. And then on this integral right here, I can use my traditional integration by parts here. We can call this piece u, and we can call this piece dv, and we can do our integration by parts that way. If you don't remember what that is, we have the integral of u dv is going to be equal to uv minus v du. The v here we get by integrating here. We have dt equals dv. Integrating those, v is equal to t. And we're evaluating that from 0 to 1 also. Over here, this integral is going to be from 0 to 1. And we have v. V is t. We're going to take the derivative of log t squared, which is going to give us 2 log t inverse dt. All right. Then we can clean this up. The t's are going to cancel here. We can pass this 2 through the integrand, and we can evaluate over here. This is going to be a 0 contribution again for the same reason the last one was a 0 contribution. The only thing that's different is the power has changed from a 3 to a 2, and we're going to get the same 0 contribution here. I've moved everything up so we can continue to work on this. we need to simplify some things. We need to evaluate this piece, and we need to clean up this integral. So first of all, evaluating over here, if we plug 1 into this, this is going to go to 0. If we plug 0 into this, this also goes to 0. So we have a 0 contribution coming out of that. As we look over here at this integral, this t and that t are canceling. The 2 we can move through the integral. So we are left with this. All right. Now we can integrate this of t log t minus t evaluated from 0 to 1. And that is being multiplied by the negative 2 on the outside here. I'm going to go ahead and ignore the 0 now. Outside of this, we have the negative 3. And then outside of that, we have the negative 1 to the 3rd power. And this is, again, all equal to this, which is our essentially our original integral that we are trying to solve. As I evaluate this, as we substitute 1 into here, this piece is going to 0 again, but this is going to be 1. So we end up with negative 1 there. As we plug in 0 here, this and this are both going to 0, so we're picking up a negative 1 here. All right. Now we have 4 negatives here, so our answer is going to be positive. And then we have 1 times 3 times 2 times 1. This is a positive 6, meaning that our original integral is equal to 6, which was the anticipated value that I was looking for. I hope that there has been some value in this for someone. I know it's been an experience for me to help me work through some things that I wasn't sure of at first, like how to attack this, work through deriving this, improving this, and then some of the other mechanics that are here. Hopefully you find some mathematics in your part of the world to enjoy. Cheerful calculations.